1974. A YF-16 prototype accidentally lifts off the runway. It wasn't the pilot, it was by design
Structural
deliberately
integrity
unstable.
of the YF-16.
Why build a jet that wants to fall off the hill? Because in a dogfight, energy is life. This is the insane engineering of the F-16.
Softly, slowly, there, it's flying.
Here's the plan. We start with the problem Vietnam exposed. Big, fast jets losing where agility mattered most. Then we go to the doctrine, the energy maneuverability, idea that treats speed and altitude like a bank account. From there, design. The pitot chin inlet, strakes, and auto-LEF, digital flyby wire with relaxed stability, side stick, and that 30-degree seat, how each choice cashes in on physics. Next, proof. Real EM charts and a timed 360-degree turn, every number shown with a conditions card. Finally, relevance. Why the Viper still bites today, seed with harm, modern AESA, and auto-GCAS saving lives. No fluff, no mystery, just clean engineering told from a pilot's seat. If you like understanding why something works, you're in the right place. On paper, the F-4 Phantom was a monster. Twin engines, Mach, 2-, a radar that could see and shoot far, and the legs to bring a lot of missiles to the fight. But paper doesn't turn if the jet can't. Down low and within visual range, the Phantom bled energy fast. Its wing loading spiked. Rearward visibility was cluttered by frames, and those smoky J-79S rode a black arrow to its position. The MiG-21 flipped the script. Small, light, single engine, a razor-thin delta wing. GCI controllers would run it under the radar, pop it up for a single pass with an infrared atoll, then yank it around and vanish. The fight compressed into seconds, where agility and energy management decided everything. Loss exchange ratios swung in uncomfortable ways during certain periods. Sources differ on exact numbers, but the trend was unmissable. When the fight went WVR, the side that managed energy, surprise, and nose authority better tended to win. The US response wasn't just to buy more thrust, it was to study. The multi-volume Red Baron analysis pulled apart hundreds of engagements. It hammered home a few truths. The first visual tally often wins. Surprise is a weapon. Training had to include dissimilar air combat. Missiles needed to work better at real ranges and off-bore sight. And critically, pilots needed a jet that could turn and keep turning without falling off the energy cliff. Out of that came a sharper question. What if we designed a fighter from physics up to win at the altitudes and speeds where fights actually happen? That question birthed the lightweight fighter program later formalized as the Air Combat Fighter. Two prototypes took the stage, General Dynamics YF-16 and Northrop's YF-17. The test cards focused where Vietnam had exposed the gap. Transonic acceleration, sustained turn, climb, handling qualities, and yes, cost and supportability. This wasn't a beauty contest for top speed. It was a search for a jet that could own the 0.8 to 1.2 Mach regime, cashing in energy like a pro, while giving pilots visibility and control to actually spend it. By design, both prototypes were compact and purposeful, but one of them consistently showed the right kind of excess power in the band that mattered, and did it with the kind of handling that lets a pilot live at the edge without fighting the jet. On the 13th of January 1975, the U.S. Air Force picked the YF-16 for the ACF, not just for how it flew, but for how it could be bought, maintained, and built. Europe signed on Belgium, Denmark, the Netherlands, and Norway, kicking off a co-production venture that would seed a global fleet. The YF-17 wouldn't be wasted. It evolved into the U.S. Navy's Hornet. But for the Air Force, the path was clear. A single engine, lightweight fighter optimized for the transonic fight. Condense the problem into requirements, and the outline of the Viper appears. Bubble canopy visibility so a pilot can find and keep tally. A wing and flight control system that trades angle of attack for turn rate without punishing energy loss. A cockpit that lets hands stay on throttle and stick while the jet stays within safe limits automatically. And an airframe that's affordable enough to buy in numbers and light enough to actually feel like a fighter. Vietnam didn't just change the tally, it changed the questions engineers asked. Instead of chasing headline Mach numbers, the design pivoted to the physics of maneuver where lift, drag, thrust, and weight meet time and pilot workload. That pivot will take us to energy maneuverability and to the choices that made the F-16 feel less like a machine you fly and more like a jet you wear. So, The problem statement is set. Build a fighter that wins where fights actually happen, and make it simple enough to keep flying, training, and upgrading for decades. Next, the doctrine that turned that mandate into math. Let's build the map of a dogfight from scratch. Horizontal axis, Mach number, how fast you're going. Vertical axis, turn rate, how quickly you can swing your nose. Every dot on this chart is a trade between lift and energy. At low to medium speeds, your lift limited, the wing runs out of grip before the structure runs out of strength. Push faster, and you hit the G limit first. Somewhere in between lies the corner speed, the fastest way to turn without bleeding more than you must. That's instantaneous turn, what you can do right now. But a fight isn't one snapshot. It's a string of seconds where energy leaks or refills. That's where sustained turn matters. Enter specific excess power, Ps. Think of it as energy income per unit weight. If Ps is positive, you can climb or accelerate while turning. If Ps is negative, you're spending faster than you earn. You'll have to trade altitude or slow down. Ps equals 0 is the razor's edge, the sustained turn you can hold without losing altitude or speed. EM, energy maneuverability, stitches these ideas together. It doesn't care about brochure top speeds. It cares about how quickly you can change direction and still have the energy to do it again 5 seconds later. Here's the fat band Mach, 0.8 to 1.2. Transonic. It's ugly for drag, brutal for pilots, and real for combat. This is where merges happen, where missiles get notched, where a second chance comes only if your jet can cash in energy efficiently. Think of stability like a ball on a landscape. Put the ball on a hilltop, the smallest nudge, and it rolls. That's unstable, quick to change. Drop it in a valley, push it, and it comes back. That's stable, forgiving but resistant to rapid change. Fighters trade between these behaviors. A jet that's slightly relaxed in stability, carefully managed by computers, can turn faster with less input. You get the nose where you want it now, and the system helps you not pay for it forever. In practice, you pounce with instantaneous turn at or near corner speed, then settle onto the Ps equals 0 ridge to sustain. If you can't sustain, you'll bleed down into a trap. Slow, nose high, out of options. EM turns that trap into a number you can design around. So what? EM isn't a poster on the wall. It dictates design. If the fight lives in the transonic, build an inlet that behaves cleanly there instead of chasing Mach 2 vanity. If high angles of attack will save you, shape the forebody with strakes and let auto-LEFs keep the flow attached. If energy must be spent precisely, give the pilot digital fly-by-wire with relaxed static stability, so the jet does the hard math and caps G and angle of attack for you. And because the human is part of the loop, recline the seat 30 degrees and put a side stick on the armrest, so a 9G pull doesn't steal the fine control you need. Notice what's missing, chasing a bigger number at the top of the brochure. EM pushes you to optimize where you fight, not where you pose. That's the intellectual pivot from the Vietnam era. Stop paying weight and drag for speed you don't use. Pay for agility you can bank. From here on, every feature we show you pays interest in EM terms. Some of it looks subtle, an inlet lip, a flap that moves itself, a computer that says 9G is enough. But together they reshape the chart where it counts. That band between 0.8 and 1.2 Mach. That's how the F-16 converts physics into an edge you can feel in the seat and see on the timeline of a fight. Doctrine framed the problem. Now let's look at the hardware choices that make the Viper live on that map. Design starts at the mouth. Older fighters like the F-4 and F-15 use oblique shock inlets, cheek scoops with a wedge to step down supersonic flow. The F-16 puts a pitot, normal shock chin inlet under the nose, a cleaner, fixed geometry that behaves beautifully in the transonic band. We actually fight in Mach 0.8 to 1.2. Past about Mach 1.2, it's not the most efficient choice, and that's a trade the Viper accepts, on purpose. Right above the lip, a boundary layer diverter peels off the slow, turbulent air that rides the fuselage. That keeps the fan face from seeing a stutter one blade in molasses, the next in free stream, which would pound the compressor with alternating loads. Smooth flow in means predictable thrust out, especially when you're pulling high angle of attack. Putting the inlet under the belly solves the starvation problem at high AOA, but it creates ground ops headaches. You can't fling debris straight into the engine. So the nose gear rotates 90 degrees into a flat bay, and the main gear swings out to widen the stance. The gear wells sit immediately aft of the inlet-tight packaging that only works because the wing is thin and the fuselage carries the load. All of it adds up to a jet that can taxi, take off, and land without sandblasting its own engine, yet still breathe cleanly when the nose is pitched high and the pilot is busy. As the program matured, the inlet grew options. Early jets wore the NSI small mouth that matched Pratt & Whitney engines. When the GE F-110 arrived with bigger airflow appetite, the MCID big mouth showed up. It's the same philosophy: pitot chin inlet scaled to feed different engines without rewriting the whole airframe. Breathing is half the story, lifting is the other. Those long leading-edge strakes aren't just for looks. At high angle of attack, they shed strong vortices that run over the wing, re-energizing the boundary layer so the flow stays attached longer. Translation: the jet keeps making lift deeper into the turn instead of quitting on you. The F-16 adds brains to that brawn with automatic leading-edge flaps. The flight control computer reading Mach, AOA, and G moves the LEFs for you, delaying stall and trimming drag in the transonic band. No switchology mid-merge. The jet does it, and you just get the turn. There's a packaging trick here. The wing is thin, great for drag, tough for mechanics. To muscle the LEFs at high dynamic pressure, the system parks a hydraulic drive inboard and sends power outward through torque shafts, around an angular gearbox, and into rotary actuators near the hinge line. It's compact, stiff, and robust because the worst time to lose a leading-edge device is mid-turn at 9G. Net effect? In the 0, 8, 1, 2 Mach trench, the wing behaves like it's got more grip than its thickness would suggest. You feel it as nose authority that stays with you rather than evaporating the moment you pull. Design is trade space, but it's not random. Every choice points back to the EM map you saw earlier. If the band you care about punishes sloppy inlets, you pick geometry that stays predictable there. If turns are won with controlled AOA instead of brute speed, you invest in vortex lift and automatic leading edges. If your lifeline is a single engine right under your chin, you keep foreign object damage out of its mouth. The beauty of the Viper isn't that any one feature is futuristic. It's that the whole airframe is bent around one idea: turn fast, spend little, recover quickly right where the fight lives. The chin inlet feeds clean power in the trench. The strakes and LEFs make a thin wing act big when you need it. The landing gear solves the compromises that inlet placement creates. That coherence is what you feel in the seat, a jet that seems to want to maneuver. Next, we'll wire the pilot into that airframe. Digital fly-by-wire, relaxed stability, and the human factor choices that let you actually use everything the aerodynamics just bought. Time to put numbers on feelings. Same altitude, same air mass, clean configuration. The F-16 and the F-4 each draw an energy maneuverability portrait. Look for two things: where the instantaneous turn spikes your corner speed, and where the P's equals 0 ridge sits your sustained reality. At or near corner, the Viper snaps the nose faster thanks to lighter weight, lower wing loading, and the way LEFs and strakes hold flow at higher angles of attack. Slide to the P's equals 0 ridge, and the picture holds. The F-16 can sustain more turn in this 0.8 to 1.2 Mach band without paying a steep an energy tax. Let's make it tactile. Same conditions, same start. A timed 360, not a stunt. A proxy for how quickly you can bring weapons to bear and how much energy you have left when you do. Result: under these example conditions, the F-16 completes the circle in about 25 seconds. The F-4 takes about 36. 11 seconds is an eternity when heaters are on the rail and the merge is messy. And remember the condition card. Change altitude, fuel, or stores, and numbers move. The trend doesn't. Translate that back to EM. A higher instantaneous spike gets your nose there. A stronger sustained ridge lets you stay there without falling into the slow, nose-high trap. That, in physics, is the Viper's promise. Reality check. Most fights today begin BVR beyond visual range, with networks, data links, jamming, and long-range shots deciding who gets to merge at all. But when a missile is notched, or when the picture collapses into the visual, EM becomes your life clock again. You still need to point first, turn tightest, and not run out of energy doing it. Cue the wild weasel roll. F-16 CJ divided by CM jets carry the AN divided by ASQ-213 HTS, a harm targeting system that sniffs, classifies, and geolocates radars paired with AGM-88 harm. That combo turns the Viper into a seed surgeon. Find the emitter, fix it, and fire. Then use the jet's energy margin to jink out when the enemy replies. Sensors grew up too. The newest Viper's the F-16V divided by block, 70/72 mount, the APG-83 AESA radar. Better detection in clutter, faster updates, more tracks, and the electronic stability you want in jamming and weather. A historical footnote worth keeping straight. The first production F-16 with AESA was the Block 60 for the UAE, flying the APG-80. Today, APG-83 is the path for new builds and deep upgrades. Not every save is about missiles. Auto-GCAS, the automatic ground collision avoidance system, fuses GPS divided by INS, a terrain database, and your projected flight path. If it decides impact is imminent and the pilot isn't fixing it, it takes the jet, roll wings, level, and pull. Operationally, it's already saved multiple pilots. That matters in the real world of G-lock, fixation, and night-low missions. Range is relevance too. Conformal fuel tanks add fuel without stealing wing stations, a quiet superpower for patrols, seed, or escort, where the geometry of the fight might stretch. You keep your weapons, you keep your drag predictable, and you keep showing up on station. Airframes don't live forever unless you help them. Through service life extension work, late block F-16C divided by D-jets get certified from about 8,000 toward 12,000 flight hours. New build block 70 over 72 target that longer life out of the box. Longevity keeps training ecosystems intact and makes sensors and weapons upgrades economically sane. Variants tell the same story in chapters. Block 30 begins the big engine split and inlet choices to match airflow. Block 40 over 42 bring Lantern and a tougher airframe for low altitude, Night Strike. Block 50 over 52 grow into the CJ divided by CM Weasel community with HTS divided by Harm. And the Block 70 over 72 the Viper many are buying today adds the APG-83, a modern cockpit and mission systems ready for the next decade. Notice the pattern. Upgrades don't chase brochure Mach. They sharpen the fight you actually have. AESA makes the picture cleaner, so you decide sooner. HTS divided by Harm declaws the ground picture, so you can enter and leave alive. Auto-GCAS forgives a rare human lapse. CFTs extend the clock without stealing pylons. SLEP keeps the fleet in play long enough to matter. And if the air-to-air picture collapses to the merge, as it still can, the Viper's EM pedigree cashes out. You point now, you sustain there, and you exit with enough energy to set up the next card. That's the through line from Vietnam's lessons to today's tasking. Proof isn't a number out of context, it's a number with context. In the band where combat lives, the F-16's design still pays dividends. The physics didn't change. The Viper just keeps finding smarter ways to spend them. The F-16 was never a Mach 2 vanity project. It's a jet engineered to win, where you actually fight in that transonic trench where lift is precious and seconds decide outcomes. The inlet, the strakes and auto-LEFs, the seat and side stick. The digital flight laws, all of it turns physics into an advantage you can feel in the seat and see on the EM chart. Today's battles lean beyond visual range, with sensors and networks calling the opening shots. But when the picture compresses, your energy clock still rules. That's why the Viper endures. It spends energy precisely, it guards the pilot from the edges, and it keeps upgrading the parts that matter. If you want to go deeper, we've built 2 extras, a bonus, energy maneuverability deep dive corner speed, PS trade-offs, and why sustained turn is your bank account, and a hands-on look at Auto-GCAS, how GPS divided by INS, terrain maps, and prediction take the jet back when seconds run out. Links are on the end screen. Thanks for flying along. If this kind of physics-first storytelling works for you, hit subscribe and check the extras. And if you've flown or worked the Viper, drop your notes below, we read everything. In air combat, energy is life. The F-16's genius is simple. Optimize where you fight and let the physics do the heavy lifting.